LEDs and photodiodes. By the end of this lesson, you should know how an LED works and how a photodiode works. The LED. An LED uses a p-n junction. Whenever an electron migrates from the n-type to the p-type, it combines with a hole. In doing so, it loses or releases energy in the form of a photon of light. Depending on the materials used to make the semiconductor, the frequency of the photon of light can change, allowing us to have different colors: red, yellow, green, and blue. The LED can only work when it is connected in forward bias. This is when the n-type side of the semiconductor is connected to the negative terminal of the battery. Note in this diagram the Fermi level does not stay flat. This is because when under forward bias, the electrons find themselves at a higher energy level than the holes in the p-type. The electrons are now able to combine with the holes very easily and allow a continuous forward current through the junction. Whenever the electron finally combines with a hole, it releases energy in the form of a photon of light. The energy of the photon of light emitted can be calculated if the frequency of the light is known. This can be done using the following formula. E equals hf, where E is the energy of the photon, h is Planck's constant, 6.63 by 10 to the negative 34 joule seconds, and f is the frequency of the light emitted measured in hertz. The photodiode. The photodiode is very similar to how an LED works, but in reverse. If you take a look at the symbol itself, you can see that actually the direction of the arrows are actually pointing inwards rather than outwards. Remember that the arrows on this symbol represent light. For an LED, the arrows are pointing upwards because it's emitting light. For the photodiode, it's actually taking in light, so the light is pointing towards the diode symbol. The photodiode reacts to light in what is known as the photoelectric effect. It takes in light energy and converts it into electrical energy. Photodiodes can operate a number of modes, but one that you need to be aware of is the photovoltaic mode. One example that uses the photovoltaic mode is the solar cell. In this mode, the diode has no bias voltage applied, which means it's not connected to a battery or EMF. Each individual photon of light that is incident on the p-n junction has its energy absorbed, producing electron-hole pairs. This is where an electron is excited from the valence band to the conduction band, and this leaves a hole behind in the valence band. This results in an excess number of electrons in the n-type and an excess number of holes in the p-type side, producing a potential difference across the photodiode. In this diagram, we have a p-n junction which is absorbing photons of light. Over here on the p-type side, you can see that electron-hole pair is being created. A photon of light has been absorbed, and this causes the electron to be excited from the valence band into the conduction band, leaving behind this hole. These electrons can then move down the depletion layer, leaving an excess number of holes in the p-type side. Over here on the n-type side, again you can see electrons are being excited into the conduction band, again leaving holes behind in the valence band. These holes then move up the depletion layer, leaving an excess number of electrons on the n-type side, and this results in a potential difference, or EMF, being created. To summarize learning intentions from the start of this lesson, we now know that an LED uses a p-n junction, and we know that whenever electrons migrate from the n-type side to the p-type side, the electron combines with a hole, as a result loses or releases energy in the form of a photon. We know that the photons of light can have different frequencies and also have different colors: red, blue, yellow, or green. We're also aware that this energy can be calculated if the frequency of this light is known. We also know that a photodiode works almost in reverse to an LED. Where light is absorbed by the photodiode, this actually creates electron-hole pairs. So literally the electrons are being separated from the atom, leaving a hole behind. When this happens, this creates an excess number of holes in the p-type side, an excess number of electrons in the n-type side, and thus creates an EMF or potential difference.